Good morning. My name is Ashwin Vijay Shankar, and I'm presenting the Apex Sentinel Array, a vertically integrated planetary defense and orbital sustainability architecture designed for deployment on a mature space elevator infrastructure. This proposal does not attempt to solve the material science challenge of constructing the space elevator itself, but assumes that a mature space elevator complex is already existent. It assumes also a functional carbon-based tether system extending from Earth's equator to a counterweight beyond geostationary orbit and focuses on how such permanent infrastructure can be used to transform into a continuous orbital defense and industrial ecosystem. The central philosophy of the Apex Sentinel Array is not speculative futurism but systems convergence. Each subsystem described today traces directly to ongoing research in superconducting materials, cold atom interferometry, neuromorphic computing, pulse power electromagnetic launch, advanced photovoltaics, continuum robotics, and laser based material processing. Innovation lies in not inventing new physics but in coherently integrating advanced technologies into a scalable orbital architecture. The space elevator extends approximately 40 to 45,000 kilometers from the Earth's surface to a counterweight beyond geostationary orbit. At this altitude, centrifugal acceleration balances gravitational attraction, maintaining continuous tether tension. The counterweight region experiences outward radial force proportional to the distance from Earth's center, making it structurally ideal for mass-intensive infrastructure. The Apex Sentinel array is mounted beneath this anchor as three vertical separated modules. This separation is deliberate as high energy defense systems are isolated from computational control cores. Industrial processing is isolated from electromagnetic launch systems. Structural vibrations and electromagnetic interference are prevented from cascading along the compartments. The architecture is designed around containment, redundancy, and fault isolation. The first module houses a high temperature superconducting electromagnetic railgun designed for kinetic deflection of hazardous near Earth objects. The railgun operates on Lorentz force acceleration, and when a conductive armature bridges two rails that carry a high current, it experiences a force proportional to the product of current and magnetic flux density. With superconducting rails, resistive heating losses are drastically reduced, enabling sustained mega ampere current pulses over millisecond durations. Electromagnetic launch systems have already been demonstrated at multi-megajoule scales in naval and laboratory research environments. The Apex Sentinel array scales this principle to orbital defense deployment through pulse power energy storage. Probably a representative defense shot consists of a tungsten impactor of 10 to the power 4 kilograms, accelerated at 11 kilometer per second. Assuming a 40 to 50 percentage conversion efficiency, the required stored electrical energy per shot is approximately 1.2 to 1.5 terajoules. The station maintains 20 terajoules installed storage with 15 terajoules operational reserve, enabling approximately 10 full power shots before recharge. Energy is accumulated through a 100 megawatt multi-junction solar array and stored in layered bulk storage combined with superconducting magnetic energy storage for rapid discharge. Recoil forces align along the tether axis and remain negligible relative to orbital mass scales. All firing authority remains human gated. Mounted at a upper anchor are cold atom interferometric gravity gradient sensors. Cold atom interferometry exploits the wave nature of matter. Atoms cooled near absolute zero are placed into coherent superposition states. When recombined phase shifts induced by acceleration and gravitational gradients are measured with extreme precision. Research programs at NASA's Jet Propulsion Laboratory, the European Space Agency, and multiple quantum laboratories have already demonstrated space-compatible cold atom systems. Within the Apex Sentinel array, these sensors measure minute variations in local gravitational gradient and station acceleration. They enhance orbital state estimation, improve modeling of subtle perturbations, and increase trajectory prediction confidence. When fused with conventional radar and optical systems, they do not replace, they enhance orbital state estimation, improve modeling of subtle perturbations, and increase trajectory prediction confidence when fused with conventional radar and optical systems. They do not replace radar or optical tracking, but they augment them. Complementary systems include multi-band radar, synthetic aperture radar, optical and infrared telescopes, hyperspectral classification sensors. All sensors feed into the neuromorphic AI core where probabilistic fusion and orbital propagation modeling occur in real time. The second module houses the neuromorphic artificial intelligence core. Neuromorphic computing architectures mimic biological spiking neural networks. Unlike traditional digital processors, which consume significant energy for parallel computation, neuromorphic systems perform event-driven processing with dramatically improved energy efficiency. Platforms such as the IBM True North and Intel Lohi demonstrate the viability of this architecture today. Within the Apex Sentinel array, the AI core operates at approximately 50 kilowatts under nominal load, processing sensor fusion, orbital propagation, elevator traffic coordination, structural health diagnostics, debris prioritization, and defense modeling. Debris capture is performed using bio-inspired continuum robotic micro tethers inspired by tentacle-like ciliary manipulation systems developed in advanced robotics laboratories, including research at MIT. These compliant robotic arms distribute bending along their length rather than relying on rigid joints. This reduces impulse transfer during contact and minimizes fragmentation risk. Priority removal focuses on large intact derelicts, rocket bodies, medium mass debris, known to contribute significantly to cascade probability. Modeling studies show that removing even 5 to 10 high risk intact objects annually produce measurable long-term reductions in collision probability growth. Additionally, damaged but intact satellites can be stabilized for potential recovery or refurbishment, preserving economic value and reducing redevelopment time. The economic justification of this module is rooted in risk avoidance. Preventing a single catastrophic satellite collision can avert losses ranging from hundreds of millions to billions of dollars. Insurance risk reduction and asset preservation far exceed the operational cost of debris capture. The AI core is radiation hardened and segmented into redundant computational domains. Continuous state verification and checking occur between onboard AI system and a ground-based AI counterpart using high bandwidth optical laser communication, similar in principle to NASA's demonstrated laser communication systems. At the peak, human override remains embedded at all critical decision layers, particularly within the defense subsystems. The Module 3 provides docking, industrial processing, and tether maintenance. The third module provides logistical and industrial capability. Docking interfaces support elevator climbers and spacecraft operations, and hybrid magnetic assisted stabilization is achieved through interaction between conductive tether pathways and onboard superconducting coils, reducing mechanical wear and enabling partial regenerative energy recovery during descent. Laser-based in-situ resource utilization enables controlled thermal separation of carbon-rich residues from captured debris. Carbon products are converted into ablative re-entry materials when necessary, while metallic mass is transported via elevator for terrestrial refinement. A defining structural feature is continuous tether reinforcement, where during descent, climbers deposit thin carbon-based compounds onto the tether surface, sealing microfractures and mitigating long-term fatigue and radiation damage. This establishes a positive maintenance loop. The more the elevator is used, the more it reinforces itself. When it comes to the anchor station, it generates approximately 100 megawatts using advanced multi-junction photovoltaic arrays with assumed future efficiency near 50%. Required array area is approximately 0.2 to 0.35 square kilometers, with baseline station load is approximately 1 megawatt. Net charging capacity enables 1.5 terajoules per railgun shot and 15 terajoules per 10 shot reserve. With this all, it takes approximately 42 to 45 hours of full recharge time. Energy architecture isolates all discharge from base systems to ensure grid stability. When it comes to the Apex Sentinel array, it is not a singular device, but rather it is an integrated orbital systems architecture combining superconducting electromagnetic launch, cold atom gravity sensing, multimodal radar and optical tracking, neuromorphic AI control, continuum robotic debris capture, laser-based resource processing, hybrid elevator propulsion, continuous structural reinforcement. Each subsystem traces directly to active research programs in the fields such as aerospace engineering, material science, quantum physics, and advanced robotics. This architecture transforms the space elevator from a transport structure into a resilient orbital ecosystem capable of planetary defense, debris mitigation, economic preservation, and structural self-maintenance. It does not rely on speculative physics, but rather it relies on convergence, and convergence is how megastructures become engineered reality. Thank you.